Hello, good morning everybody. Welcome to lesson 9 of CE 5361. And if you see a big yellow tail go across my face, my big cat has just jumped up on the table and is going to teach us how to use our computer program. Come on, big yellow cat, move over here. That way you can be in the way, but I can still do what I have to do. Very good. Unusually compliant for a cat today, so he's plotting something, no doubt. So returning to the lesson at hand. So at the end of yesterday, I rapidly fussed around with HEC-HMS, and that was just to get us started with no expectation that other than watching it, it would be terribly instructive. Today, in contrast, I'm going to attempt to work through two examples. One of them is utterly simple. The second one's a little bit more elaborate. We may not get it completed, but I think we have a good shot at it. And the second example will be instructive in that we'll be using very similar context throughout the remainder of the class. The watershed we're going to study in the second example. You've actually already seen it without knowing it. But I'm going to look at two. I have sort of a more rural one, and then this first one that we're going to see today is pretty urbanized. And there's not a lot of difference in terms of data input between the two situations, but there's considerable difference in the various processes that we choose to simulate to ask our hydrologic questions. And also, for a change today, I'm going to attempt to do it in Windows just to see if it's still working. I've been struggling with, I didn't want that to happen. You can give me my screen back? That is just bizarre. I pre-tested this. Why is it? There we go. Cool. So now we're in the Windows world. So I'm constrained to what most of the rest of the world uses for engineering productivity. We'll see how well that goes. I'll go to the E button, which I think is supposed to be my web address. Yeah. And and microscopic type even. Yeah, we may be going back to, that worked. Except I really didn't want to go to the Moodle site. I want to go to the main site. I'm remembering why I've always found the Windows operating system a little bit constraining when doing internet-based work. I just remember now, it's not very good at it. So we'll go to our class. I'm going to go and get to the lesson 9 PowerPoint file. It's only 9 slides, so if I was really fast, we could be done in 9 minutes, but that would be utterly useless. And we want to go to lesson 9, which should already be there. It's the wrong style file, but we want to go to, so let me familiarize you here. The PowerPoint we're going to look at is in the PowerPoint directory. This one called dat source ashcreek.zip has already been moved to Hydro 1 through Hydro 5. And I actually need to remind you all something when using the HydroShare websites. Because when I said to log out, I think I used bad terminology, and I noticed that Hydro 1 and Hydro 5 weren't operational yesterday. They weren't broken. One of us had visited it, and if the context of log out was what you heard on my video, then you did the correct thing. You logged out of the application, but it means you pretty much shut it down for any future use. I'm working on a workaround so that won't hamper things. But I'll remember today to show you how to exit. That's it, exit the interface. So the zip files are already there. Now what's contained in the zip files, I think, is shown right here. My God, that's miniature. Let's see if I can make this bigger. No, you can't because it's a computer. Yes, I know I'm screen sharing. Thank you very much. Well, I can't make this bigger right now. I have to do some reading on how to do it. There's a couple of R scripts, and we're going to examine those shortly because they're actually important for any kind of hydrology where you have actual data. And then there's 3 folders here. This is Ash Creek 730603, Ash Creek 750527, Ash Creek 780520. We're going to go to the 0603 because I've already processed that. And in the 0603, there is a file called rain station 08057320. So that's the station ID of that particular watershed. So there's rainfall data available, and the one with the prefix unit is an observed hydrograph that's paired with this rain, meaning the rainfall and the observed discharge were collected at the same time or over the same time period. I'm just going to briefly look. This is what these particular files look like. There's some header information, and then there's a column of date time in a prescribed structure. So this is called structured data. An hours passed column, that's the one we're going to make use of. Runoff in cubic feet per second, and then accumulated runoff in watershed inches, and we'll make use of that column. In the rain column, it's almost the same structure. Again, we're going to work on hours passed, and the rightmost column, which is accumulated weighted precipitation. This particular time series data file has precipitation from 2 gauges, gauge 1 and gauge 2, or gauge 14W and 15W. And I have no immediate knowledge of where those gauges are. I have a file somewhere that correlates those to geographic location. So that was our quick introduction to that data. And there's a file here called instructions that's actually meaningless. This is an old homework assignment from a long time ago, and the instructions are for doing the homework assignment. But I left them there because I thought I might need them at some point. See, the Excel, the script directory has copies of the scripts. These are actually quite simple, but in my opinion, incredibly important scripts. And let me get the PowerPoint file and see how this is going to work. Okay, so this is first for me. I've never tried to do this on my Windows machine at home. Hit open. It's going to see if it's secure enough. And then it goes back to the... I didn't expect that to happen, but okay. So now to the formal part of today, or the more formal. Introduction to HEC-HMS. This first part is prepared as if you're aware of the existence of HMS, but you may never have used it. If that's not true for you, bear with it, and we'll get to the actual example shortly. So HEC-HMS, the HEC part means Hydrologic Engineering Center. It's part of the United States Army Corps of Engineers. I think their main role is in facilities management. I might have that wrong. They're located at the University of California in Davis, and so that's the source of the name. And HMS means Hydrologic Modeling System. When I was in college, HEC-HMS didn't exist yet. We had a software called HEC-1, HEC-2, at HEC-5, HEC-6, and a few other ones. And they were, think of them as submodules that later on got incorporated into HMS. HEC-1 was the hydrology program. And in HEC-1, you specified characteristics of a subbasin, different processes that you wanted to simulate. You structured your input and output data and ran the program. And what came out of the program was a long ASCII report file. If there's time today, I don't have the ability to run HEC-1. I don't have a copy up and running. But I can show you what a circa 1980s output file for a professional program looked like. There was a considerable amount of post-processing that would have been required to interpret the output. In the 90s, they decided to create a user interface. Their argument was to speed up data input and enhance output interpretation. The second part of that, I think they achieved. Output interpretation, from a modeling perspective, is much, much easier in the interface. I don't think it sped up data input anyway. If anything, it helped generate billable hours because it was really easy to put the data in wrong, and it would be there, but you couldn't make use of it. It's a complex tool, and it's meant to be used by a knowledgeable and skilled operator, and I'll define that in a second. It's based on the second bullet item. You're all knowledgeable people. You would have no trouble using this. But if you're like, you'll see today, like when I do it, but if you use it and then stop using it and then go back to it 6 months, a year later, you're kind of rusty. But if you are in a situation where you get to use the tool a lot, you'll become very skilled, and you will be able to do things much quicker. And that's the point of it. It's a tool to help you do things quicker. The knowledgeable part is knowing which process models to choose and how to structure your inputs. Data management is through a graphical user interface, no surprise there. Any of you that would fall into the category of a digital native, and I suspect some of you are probably young enough to go into that category, have known nothing but a graphical user interface. It uses multiple input files, which is not the worst thing in the world, but somewhat annoying when you lose one. Produces multiple output files, also somewhat annoying, but not a big deal. It stores all of its data internally in something called the HEC data storage system, which in the 60s, when this was started, the data storage system as it exists today made sense. I would argue it doesn't make sense anymore, and it's incredibly prone to storing data and then you can't find it again, ever. I mean, it's worse than a MySQL database. All files are organized into a thing called a project. That's at least a saving grace. A project, think of a project as a directory that contains all the files in a particular model. A model being the file collection and the HEC-HMS software to operate on those files. Within a project, it maintains paths to the individual files. So if the files physically aren't located in the directory, or logically are not located in the directory, but their symbolic links are, the second bullet item can't be done. You can package it up and email it, but if it's just a symlink, it won't run elsewhere. But if the files are indeed stored in the appropriate project directory, then it's quite easy to mail entire projects and have them run elsewhere, and that's important. So HEC-HMS itself conceptualizes precipitation, watershed interaction, runoff into major elements, and the three we mentioned yesterday are a meteorological model, a time series model, and the simulation control features. Let's see, there's one other. I don't have a basin model on this, but the basin model is the other thing that has to be there. The time series models are optional. Basin models not. Meteorological model is how we describe the rain gauges and assign rainfall to different subcomponents. Time series are how we would supply input hydrographs, and we'll do that today. And also how we supply observed hydrographs for the calibration exercise. And then simulation control is where we tell what, when, and how to simulate. A hydrologic situation is conceptualized as a basin comprised of subbasins, and the subbasins are the things that convert rainfall into runoff. There's a loss model that takes the rainfall on the subbasin and abstracts a portion of that rainfall as loss, and the remainder is available for runoff. Not shown here, there's also some hydraulic elements where we can store water. And then there's a transformation model, and that describes how the excess rainfall is redistributed over time and moved to the outlet. And I think the first example will clarify that. So in terms of that, we have precipitation, the abstractions, I've just described that. Transformation, we actually haven't had any lessons on transformation. That comes next week, and it's just the way it fits in my thinking of how to lay this out. So today I will be providing the necessary parameters for the transformation model without explanation. And then there's routing components, so we can do watershed routing, stream routing, and storage routing. So our first example is what I call a minimal model. And this example actually has a different purpose than I would normally do to introduce HEC-HMS, but it's simple, and so that'll get us started. I'm writing down the information that's actually on the screen before you so that I remember how to do it. And then the second example will be the Creek Watershed. So I'm going to move to, see if this will work. Escape, let me out. Yeah, I'm giving up on the Windows thing. That's not going to work for me today. I need to go to our Share Hydro. Okay, so I'm going to do the demonstration today in Share Hydro DEV. That's the developer portal. So it should look very much like any of the other fives. And that way I'm not clobbering anything in the other five. Actually, it's also gives me the ability to fix mistakes as they come up. Okay, so that's working, that's good. I'm going to full screen it. And let's hope my internet connection stays fast for the next hour. So our first HMS model is going to be an SCS type storm on 640 acres, which is 1 square mile. So when we study SWIM, we'll see that the scale that the two models are intended for is quite a bit different. The area unit in HEC-HMS is in square miles. The area unit in SWIM is in acres. So they're intended for much different scales. It's not a problem. You can use SWIM for very large scale, but you need to be aware of the difference in the default units. So we want to, actually we need to pre-process the data. So I'm going to the HEC-HMS model directory. All of the repositories should have something almost identical to this. The Share Hydro 1 through 5 might be missing Hardin Creek, MyMap, and HEC supplied examples, but it should have Ash Creek. And I'll open the Ash Creek directory. There's the zip file. You don't need to do anything with that. because this one called Ash Creek Data is the zip file extracted. Okay, back. I'm going to move that. Actually, I'm not. I can just open these. I'm going to prepare these data. So HEC-HMS wants time series data in uniform increments. So if we want, it wants data every 15 minutes or every hour, whatever you choose. It can be coaxed into handling non-uniform time increments. For example, you have an observation at hour 1, another observation at hour 2, another observation at hour 2 plus 15 minutes, another observation at hour 3 plus 40 minutes. That can be managed using the DSS editor. But when I used to teach HEC-HMS as a professional development course to state employees, I could only demonstrate that live one time out of 3. I had a 30% success rate. Usually I would do a single thing wrong and it would clobber the whole. And so over the years, I concluded that it just works better if you can get everything into a uniform time step. So let's look at, I don't want to open that one. Let's look at the rain first. I've already shown this, but I hope this will be a good example. Come on, there we go. The column hours passed. Somebody's already processed these date and time stamps and determined how many hours from the first one have elapsed. So the first one by default is always 0 hours past. Our next observation is at hour 1. Next observation is hour 1.5. You can see that the time increments aren't always the same. Like here between 5 and 6, that's an entire hour. Hour 6 and 6 1/4, that's 15 minutes. And so that's not terribly usable for HMS. So we need a way to convert it into some uniform time increment. Here's an example of an output file that meets that goal. Except that one's very damaged, it looks like. Yeah, we're going to need to rerun that. But here we have it looking 15-minute time increments. So that's what we want to achieve. I can tell you and save you the trouble. In the olden days when we would normally treat that with Excel, it was not easy to fully automate that. There was a lot of moving columns and rows back and forth. So for a long enough file, it was functionally impossible. So what we can do instead is we'll take these two R scripts. Let me copy them and paste them into this directory. And then we will examine them one at a time. We'll first do the rainfall. Possibly in our lifetime. I need to come up with a better catchphrase than that. Here is a very simple in terms of how many objects are in it, R script. So it's going to, let's go look at this shortly. It's going to clear its environment, and then it's going to have an object called the input file. And in this case, we're going to use that ASCII file as the input file. It's clearing some other objects to be sure that there's nothing in the environment. And then it's going to read the file. It's going to attach the headers to the individual file elements so that it can be accessed. Essentially, it's building a data frame. Then we figure out how long the file is. We'll create an object called elapsed time that's going to go from 0 to the total hours passed. In this case, I've chosen a time step of 0.25. Then it's going to use a built-in function called the approximation function. And what it's going to do is it's going to take this elapsed time, which is every 15 minutes, and it's going to interpolate in the hours passed in the accumulated rate of precipitation file a value at that elapsed time. And then it's going to send it back as object X for time, object Y for weighted precipitation. And we're just plotting it to be sure it makes sense. It did it correctly. Then the last part is to create an output file, and we're going to write the output file to an ASCII file, and then that will be later on you cut and paste into HEC-HMS. So I'm going to set the working directory to the source file location. That too can be automated. So as the file names change, all we have to do is change this line right here. So it's set in the correct working directory. Here goes nothing. Okay, so this error right here is not a deal killer because I'm pretty sure it created the output file. Let's check. Oh, it did not. That's unusual. And it doesn't have the string package loaded. Let me find that. Oh, rats. I failed to test this before I inflicted it on you. Need to find the R string package. If I can find it, I'll remember the name. I think it's called string R. I seem to recall that, so I'm going to go ahead and hit that. We'll know in a second. And with some luck, we only have to do this once. Or I only have to do it once. Okay, so the string package install worked. And this is the rainfall input, and this is accumulated input. So at the beginning, there's nothing very interesting happening. We get a period of rainfall here over a few hours, and then pretty flat. Then another period of rainfall here over a few hours, and then pretty flat. And then another one, fairly intense one here, between hours 22 and 26, and then flat line. So our rainfall hyetograph would be expected to have 1, 2, 3 identifiable peaks in it. Let's verify the output files there. And it is not. Oh wait, I've refreshed the folder. That's seriously weird. That worked. Well, it's a shared environment. There's no guarantee it's going to work quite how we expect it every time. Interesting, it seriously did not write the output file. That kind of is a... Alright, we'll try this one more time. I thought this would have been a lot easier. Interesting, it failed to force the install. We'll do that just after we clear the environment. Damn it. Okay, let's install packages, and I think it's all right. It's really bizarre. It's just not functioning correctly. Okay, so I will remove that. I will attach these. It's worked great on my home computer. It's literally skipping inputs. Okay, we did the plot. And it can't do the out file. So I can modify this the hard way. If it would actually take input. So I actually have to get this to work. I can't complete the demonstration. So you get the wonderful thrill of watching the program as fast as I can in hopes that, this is called out file. And its name, I think I want to use rain 15 minutes. This is not the preferred way to do it because we've de-automated everything. But this, I think, should work. So let's try to run the whole thing. Okay, did it do the output file? It did. Oh, thank heavens. Let's go look at the output file. 0.25. Excellent. So now I will, I'm not going to delete that. I need to open a new file. No, I want to open a file. I want to open the rainfall. And I'm going to have to do the file, open file, interpolate discharge, open, And we'll have to play the same game here. So we need to copy the output file name. Copy. And you will discover when you use modern software, so they've adopted this idea of very basic software and you install packages. As you can see, I just presented an example. It just doesn't work right. I've tested that for quite a while, but there's nothing I can do about it. So this should now process the output file. Let's go ahead, excuse me, the hydrograph. Let me go ahead and delete all these plots. So the plot's going to look it should look kind of the same, except it'll be different in time. Let's go ahead and run it. And save that. Here's our output hydrograph. If you look at it, it looks very much like the rainfall input, which makes sense because the rainfall drives the hydrograph. Let's verify that we have a usable output file. Which is right there, the unit file. We'll open that. And hour 0, 0.255. So these are on 15-minute increments. This is unusual flow because this is accumulated flow in watershed inches. You've multiplied that by the area and some unit conversion factors to get it into cubic feet. Okay, so we're now ready for that. Now we'll return to where I was. So don't save. All right, so now let's go ahead and launch HEC-HMS. And we're going to do the simple example, and then we'll do the Ash Creek. We've prepared the data now for the Ash Creek example. And there is our interface. Make it big enough to see. A little bit more real estate management. Okay, so this one we're going to create a new project, and I'm pretty sure it's going to ask us some. Oh, that's not what I expected, but that'll work. So this is going to be called example 1. And this is a I'm going to call this a minimal model. I'm going to use US customary units because that's what I'm familiar with, and I don't want to save it in my documents. I'm going to prescribe the save location, which will be on my desktop in HEC-HMS models, and I'm actually going to have to create a folder. So I've created a project, it's ready to go. Now we need several components. We're going to need a basin model, so we'll go ahead and create that first. And I'm just going to use the default name. No comments necessary. And then in that basin model, I'll have a single sub-basin. Put it right in the middle where I can't miss it. Hit create. A little bit more working real estate. There we go. That's how I like to see it. U.S. customary, no sediment, no missing, no local flow, no flow ratios. So this, I think, is ready to go. Let's turn back to the selection tool. We'll select the sub-basin. 1 square mile, which is the same as 640 acres. And it's the only thing we have to have, but I'm going to do a couple things. No loss model, no transformation model, no base flow recession model. So that's a very interesting basin. It's 1 square mile that whatever rainfall comes in immediately goes back out. And I don't have a reference flow, so I believe my basin model is created. Now we'll go to the meteorological model. And I want to create a not specified graph. We're going to do a project storm. And we'll now parameterize this project storm. Okay, so we have 640 acres. If I put 1 inch of rainfall on that, I would get the equivalent of 640 cubic feet per second coming off that watershed, at least at one moment. So I'm going to put 10 on it, which would be 640 feet per second, and wait, there's something wrong here. That maybe it's not the. I keep forgetting what the thought I figured this out yesterday. It's hypothetical storm is the SCS method. Yeah, there we go. I'll put 10 inches of depth. And we'll do a type 2 storm. That really concentrates it. No area reduction. We're done with that. Next, last component, I'll put a control specification. So we'll start 01 June 2020. We'll go for 24 hours. The other 24 hours. Start at midnight. Hopefully this will work. So the time specification is really vital in HEC-HMS, and it's very unforgiving. So usual errors that occur in the initial creation of a computer, of an HEC-HMS model, are timing this specification. It has to be in calendar and clock time. It does not do elapsed time. Now you'll see how we hack it with those time series when we get to that point. So this project is basically ready to go. Now all we have to do is create a compute run. And we will attempt to run it. So before I actually make the run, assuming I don't get error messages, so I may have missed something. I'm putting 10 inches of rainfall onto 640 acres. There is no loss model, so I should get the equivalent of 10 inches back out. And it should also mimic the pattern of the rainfall distribution. And, okay, so let's look at the error, because this is common. Meteorological model is not set to work with the basin model. And that's its way of telling me I've never told it to put the rainfall onto the subbasins. I just did there. So include subbasins, yes. And the basin model name is selected. Let's try it now. Okay, so I'm going to look at the graphical output. And there's my rainfall coming in. Remember, we have 10 inches, and our peak discharge is should be 6,400 CFS, give or take, and we get 7,000 coming out for 1 instant. So that's the simplest model And what I'm trying to convey here, or what I want you to see here, is that the input and the output essentially look the same. They're scaled different by the basin area and by different units. We can learn more with the global summary table. Okay, so drainage area square miles, our peak discharge was 7163 CFS, and our volume in was 9.99 inches. And there is a way to get the output volume and the input volume in the same units. And if we were to do that, we would discover that their identical input and output are the same amount, which is what you would expect in a case where there's no transformation, no losses. Okay, that ends that example for the time being. So I will go ahead and create a new example. This one we're going to call Ash Creek. Example 2. Actually, I'm just going to call it example 2, and I'll store it in Ash Creek. So we tell it where to store it. I have to do this every time. This is really quite, at some point it gets to be a nuisance. Onto the desktop, make HMS models, Ash Creek. I will store it in the same directory as the data. Create a new folder. I hope I did that right. We'll know in a second. So hit create. Oops, I just screwed up the units too. There's supposed to be a way to change that. Help won't work, unfortunately, I bet. I didn't think so. Okay, how to switch units. The easiest way is just build a new project. That was my mistake, because you've got to remember to switch the units. I believe there's a way you can set it to always use US customary. And the reason I need to use US customary in this example is that's what the example's set up as. Take HMS, go to Ash Creek data, example 2, what's the name of my project? Yeah, I think I should be able to clobber the existing one. Let's see what happens. Oh, sweet, okay, that was a win. Warning, okay, that's fine. So we've got a warning. Now let's go ahead and create our basin model manager. We'll create a new basin. I'll just take the defaults and I'll be done. In that basin, we'll need a sub-basin. I'm going to put one there, and then we will take a quick look out. Here's Ash Creek. So we've seen this map here on the left, and here's a shaded relief map. So using our G3 data, we could trace this outline and have a reference rectangle and compute the area and also determine path lengths. If we compute this area, we'll come up with about 6.92 square miles. Would be I think what all of us would come somewhere around that. 6.93, 6.9. depending on who's actually doing it, but it's going to be close to that. So keeping that in mind, I'll directly enter that information into the program. So 6.12 square miles, no canopy storage, no surface depression storage. I'm going to turn the loss model off for the time being. I'm going to turn the hydrograph off for the time being. And I'll turn base flow recession off. So currently this is a very boring model. Next thing is a meteorological model. And like before, we have a meteorological model. This time I'm going to keep the specified hydrograph. And in that specified hydrograph, we're going to, there's not much to put in yet. So once we create a time series and associate it as a rain gauge, then we can connect them to the basin. And this next step is probably initially confusing, but the more I use it, the more it kind of makes sense. So there's nothing left to do there yet, except we will include the subbasins. And let's see, options. I think I'll just leave it be. We need a control specifications manager. And here we're going to do some gaming. I'm going to put this, I'm going to make an artificial start date. 01 June. And I think this is a 2-day storm, so we'll put 03. Done. Good, looks like it captured the data correctly. And time interval 15 minutes, that's what I want. Now comes the rainfall data that we processed with those R scripts. Those are stored in something called a time series. And the types of time series that we can put in are precip, discharge, stage, temperature, radiation, wind speed, air pressure, humidity. Kind of sound familiar? It should, because those are the kinds of inputs for all the processes we've discussed so far. For the time being, we're just going to choose a precip gauge. We'll call it gauge 1. We'll create it, and we are done. Now gauge 1 has to be parameterized. So it's starting from 1st of January to the 2nd of January. We need to change that time to correspond to our time, which is June. And we're going to go to 3. So this is an important step. It can be done after the fact, after you get a bunch of error messages, but it's more satisfying to do it up front and avoid the error messages. So the gauge time window and the control specification time window need to be the same for it to produce useful output in most cases. So we've created a gauge, and now here's a table where it's asking for data entry yet. We've actually prepared that data, but we need to make one more change here. We want it to be in cumulative inches because that's how the data exists. And so now it's expecting our input data. So our next step is going to be, move this a little bit down here. I'm going to open this file, and I'm going to take my 15-minute rainfall file, open that. Oh, I have a problem there. It's got 2 columns. Let's see what happens. Copy. It is not smart enough to parse the data, so we need to make a quick rerun of our analysis. I think you can see why I had this done ahead of time. Rainfall. Open with our studio. We will just write the rainfall. Boy, I hope this works. And it ignored me entirely. Okay, session. Do it again. All right, so that's ready to go. It's just going to do the object Y. Let me delete the file so it's not there. That's off for now. Reads rain, reads an out file. Did not create the file. Save it, run it again. There we go. So this is our rain gauge file. So hopefully that gives you some incentive to understand why these stupid R scripting is useful. Let's copy that. We'll try to paste it here. And we can check if it worked with the graph. And that is our rainfall graph that goes to noon on June 20th. So the other thing we can do is to see we have a lot of missing data. It's telling us there's 193 missing values, which it's not going to like very much. But what we can do is I highlighted that last value. Go fill this whole thing up. Right click, fill, and repeat first value. Choose the okie dokie. Now we have our rainfall input file structured correctly. Let's save the project so that as we break other things, we're good to go. So the time series gauge is now created. Let's go back to a meteorological model. And we need to select gauge 1 to be assigned to subbasin 1. So that's selected. We'll save everything. And at this point, I think we have something that will actually run. So let's build a computation run. And we're going to just take defaults on this. All right, here goes nothing. We'll go ahead and attempt to run and see what errors come up. Could not find precipitation gauge for subbasin 1. So they still couldn't find the precip gauge. Let's check that. So gauge 1 is assigned to subbasin 1. Gauge 1 exists. It is a time series. It's on 15 minutes. That should have worked. There's no input here for gauges. Into 3. Check, check. Specified hyetograph. Include subbasins. Go to the specified hyetograph. Subbasin 1, gauge 1. Save it, run it. Okay, so there's an error in the meteorological model, and like all good things, it doesn't tell me what the error is. It just tells me I'm on my own. Specified hyetograph. Let's run that to default. Gauge 1. Do not know what the error is, so now we're doing the definition of insanity. So I'm going to take about 10 more minutes and try to debug this. In my opinion, it's not accepting one piece of input, and I have to figure out how to make that happen. And it's in the meteorological model. It's not doing that correctly. So it's a specified hyetograph. I've told it that. Time sequence is 1 June to 3 June. 1 June to 3 June. It's a complete graph. It's in the right units. Manual entry, 15 minutes. Done. Time window's correct. Table doesn't appear to have any offending values in it. Give it a name, not that that matters. Control specifications is correct. Meteorological model is somehow not correct. So let's do a wrong model for the time being. Oh, interesting. It literally is ignoring input. This I do not get. Area is correct. Well, that's frustrating. There's no reason why that shouldn't work. Delete the simulation run. Let's try to compute a new one, create a new one. Run one. Be nice if I could see that. Next. Finish. No hyetograph. Gauge. Well, it's being rather disobedient on input. I'm going to just save the project, exit, and start over. Okay, so that was preserved. See if it preserves the change. It did. Okay, so there's a slight chance it'll work correctly this time. That's kind of annoying that you have to exit the program and restart it. Yay! Fail. HEC gauge has 192 missing values. It's kind of hard to believe because we just went and put them in. Error. 92, well. I am going to conclude the call because we're out of time. And we will pick this up again Monday. I will diagnose what is wrong with the computer program and figure out the workaround. If you install it on your own computer, probably what I demonstrated will work just right. This has something to do with running it on a remote computer. It also has something to do with the software being free to the end user, which means it's guaranteed to break in ways that they never imagined. I want to thank you for your time. I want to wish you all have a great weekend. I've not posted an exercise set 2. I won't do that until I have a successful running HEC-HMS project to inflict upon you. And so if I get to it by the end of today, I will send you all an email message to let you know of its existence, but you'll have plenty of time to do it. So with that, have a terrific weekend, and I will slowly disconnect so that if someone wants to ask a question, there's time. Okay, well, have a great weekend, everybody. No, the blue. Morning. Never works. What file is this?
film. Okay. We're at 48 missing one invalid values. No, under film.
All right. I was fortunate enough to let the recorder running, and I very quietly just got the program working. What I think my mistake was during the lesson was that when I was creating the run model over here in create compute run, I was keep hitting the forward, but I had never selected the pieces. So if we look in this thing, the run model has to have the basin model, the meteorological model, and the control specification model existing, and not have incompatible allocations there. So now I've rebuilt the model. I'm afraid that was all in silence because I didn't know I had the recorder on. And we ran it, and it produced the output that I expected. If you recall, when we were examining the data, there were supposed to be 3 distinct peaks of rainfall, which there are, actually kind of a fourth here, and that would correspond to 3 distinct peaks in runoff. The next step would be to look at the runoff data and plot that on the same axis and see how good this model does. So I will do that while I have the recorder still running before I run out of disk space. I think I got about 20 minutes of disk space left. That won't be a problem for y'all because I'll edit it by the time I upload it. So if I return back here and look at this output file, that's still 2 columns. So I think I want to rerun those, but I want to make a quick check here. So I go to my time series data manager, and I think, and do I double click on it? I'm trying to remember how to add a new time series. Naturally, that's not going to be, oh, I go into the data manager, my bad. Component, time series data manager. I'm going to add a new discharge gauge. We're going to call that observation gauge 1. There you go, Nico. Hit a create, and we're done. And so now we should have a discharge gauge, and we will modify the gauge to have the same time window. And I think I want to have it in, it's going to have weird units. Currently the data file is not compatible because I'm pretty sure the unit is watershed inches. So we would modify our program to catch the runoff column in cubic feet per second. That's almost trivial. Let's get the right one. Open with RStudio. So we want to get which column is runoff. So in our RStudio script, we will change accumulated runoff to just runoff, and now we should be able to get runoff in cubic feet per second. So it will look like 3 or 4 peaks. And we don't need the time with it. I will save this. Set the working directory to source file location, although it should already be there. And move this up. Go back to full screen. Okay, here goes nothing. All right, there's our output file. That's what I wanted it to look like. So I will delete this sucker right here. I will delete it again. Took the deletion, delete that. I'll close that, shrinkify that, and let's look at my output file. It failed to do it correctly because, like all things, it ignored input. Hit a rerun. So we'll bring our studio back and run it again. Okay, so I made changes there to discharge. Input environment, rows, got the plot, got the output file name, and it literally ignored me. So let's destroy the file and force it to have to create a new one. Single column. Okay, so it did as desired. We're going to need that open anyway. Edit, select all, edit, copy. Come back over here to our Ash Creek, and we're now going to attempt to paste it into the window. Right click, paste. Plot the graph. There's our output plot. So if we look at this output plot and this one, they kind of look the same. I mean, it looks like this model without anything, any process model in it. They kind of agree except for the flow. Here we got 6,000 CFS, and here in the model with no losses at all, no process model, we have 12,000. So we will modify, first we're going to go ahead and plot the two things on the same axis. So the time series gauge is now correct. I believe this is now for the output, we want to go to the subbasin, options, and we have observed flow on OG1. Save it, rerun the program, and now we can see the difference. The black dots, oh, that's not right. And actually we're in spinning beach ball. The observed flow are plotted here in dots. The flow axis is all broken, so let's see what happened there. Let me save it and rerun it. I wonder if that was a consequence of just the output plotter. We'll know in a second. I do not believe the observed flow is plotting correctly. Let's take a look at the time series. Computed results. 200,000 cubic feet per second, but the data are like in the hundreds table. Where did I get a 200,000 from? I got 2,300. Oh, units. Let's try it in correct units. Rerun the program. There we go. Okay, so the black dots are our observed outflows. The blue line is the computed outflows. And there's some time mismatch, and volume mismatch. And in this case, we have no information on lag time provided to the computer program. We'll make a quick change there because we can do that really fast. Put a transform mesh method. Let's see what's the fastest one. Kinematic wave. I may regret that. Yeah, I do regret that. Let me do an SCS unit hydrograph, and I would guess about 90 minutes would be a good lag time. Save it, rerun it. Not bad on the lag times, and in fact our model with 0 losses is not a bad predictor of behavior. So at least on this particular storm example, much of the behavior is explained entirely by the time transformation required for a parcel of water that hits a remote part of the watershed to reach the outlet. Look at some global summaries. It's not a useful one. Time series. Okay, observed. Okay, volume coming out is 4 inches. Computed volume coming out is actually 5 inches. So even though the blue lines don't peak the same, there's more area under the blue curve than the black dotted curve. We'll adjust that. Let's see, 4.6, 5.2. It's about, I guess it's about 80%. So on my loss method, I'll choose an SCS curve number. And I've done this a long time, so let's try that again. SCS curve number. And if I use a curve number about 80, no initial abstraction, let's see what happens when we do that. So we make the change, and it doesn't look like it got any better, but let's look at those total depths. 4.63, 3.71, so the curve number of 80 is too small. So we can go back here and make it 90. Rerun it. 4.6, 4.77. Curve number 90 is too big. And I don't recommend you do this in practice because we're kind of twisting one dial, and there are better ways to do that. 86 is too small. 88. I'll stop at 88. 4.55 versus 4.63. We could be a little bit of anal here, and we'll increase it slightly. That's about as close as I can get jacking with curve number in this very simple illustration. The purpose of this is we've seen how to put a specified hyetograph into the model, which will come in handy. And we've seen how to put observed hydrographs into the model, and then use that to compare output, and then we could use that output to help choose parameters that calibrate the model at least to one set of observations. And then the challenge of that is, what about the next set of observations? In theory, if we have immutable parameters, we've done a pretty good job of calibrating a model to a particular watershed. We'll notice that we're missing some behavior here, getting a little bit too much there, and so it's arguable that we could mess with the transform time, make it a bit shorter, 70 minutes, run that, and that's getting better still. We still have a little bit of excess runoff here and a little bit of premature runoff there. We could possibly manage the premature runoff slightly with like an initial abstraction. I may just have broken everything. Yeah, I completely lost this peak. So I'll put that back to 0. And that will conclude the video. So thank you for your attention, and I will leave it for you to explore how to build example 2. You have this video to go by. The key thing was in building the run controller. So that concludes this video. Hopefully I can edit this correctly so that you don't have 20 minutes of nothing going on.